Hello, everyone. So last time we practiced LP modeling with Lindo and Lingo. And today we are going to talk about another type of input for Lingo, which is called the Lingo inputs with using sets. Okay. So first, I've got to tell you that compared to Lindo, the most powerful feature of Lingo is ability. I'm sorry. Excuse me. So the most powerful feature of Lingo is its ability to model a very large system using Lingo sets. Okay. So first, let me share my screen. Okay. And where's my... Okay, let me just press this. Okay. Okay. Okay, so the Lingo enables the user to create many. So I mean, perhaps hundreds, even thousands of different constraints or objective function terms by typing just several lines. Okay, the key concept that provides this power is the idea of a set of similar objects. Okay, so the Lingo allows the user to group similar objects together into sets. So the sets are simply the groups of related or similar objects. Okay. The set might be a list of products, trucks, or employees. So in the chicken feed example, such group would be the ingredients. Okay. And each member in their set may have one or more characteristics associated with it. And we call these characteristics attributes. And attribute values can be known in advance or unknown. In that case, Lingo solves for. Okay. So for example, like this, I provide three different examples. So first one, each product in a set of products might have a price attribute. Each truck in a set of trucks might have a hauling capacity attribute. And the employee in a set of employees might have a salary attribute, and so on. Okay. The sets are defined in the sets section. Okay. And the sets section always begin with the keywords sets and colon, and ends with another keywords and sets. Okay. And the sets section may appear anywhere in a model. Only the restriction is that you must define a set and its attributes before they are referenced in the model's constraints. Okay. And sets may be either primitive or derived, which means Lingo can recognize only these two different kinds of sets. Okay. The primitive set is one that contains distinct members. That is, it's a set composed only of only of objects that cannot be further reduced. Okay. And to define a primitive set in a set section, you need to specify the name of the set. And also, optionally, is member list, which is the list of members that constitute the set, and also the any attributes the members of the set may have. Okay, so for example, this set is given the set name trucks. Okay, and it contains 5 different members, right? Identified by TR1 dash, or probably dash doesn't work, TR dot dot and TR5. So in other words, that can be same as TR1, TR2, TR3, TR4, TR5. That works, okay? And the attributes for each members are called, in this case, capacity, right? A derived set derives its members from other pre-existing sets. So to define a derived set in a set section, you need to specify the name of the set and the parent set list, which is the list of previously defined sets separated by commas. And optionally is member list and the any attributes, okay? And if the member list is omitted, the derived set will consist of all the combinations of the members from the parent set. And in that case, it is referred to as being a dense set, okay? So as an example, let's consider this set section. So in this case, the product, machine, and week sets are the primitive sets, right? While the allowed is derived from the parent sets, product, machine, and week. So taking all the combinations of members from the 3 parent sets, we come up with the following members in the allowed sets. Is that correct? So here there are 3 parent sets. So 2 to 3, 2 to power 3 equals 8. So we have total 8 different combinations in this case. So this table just shows the allowed set membership, right? Okay, so okay, so when a set include a member list that limits it to being a subset of its dense form, we say the set is sparse. Okay? So the sparse set contains only a subset of the cross of the parent set and may be defined by 2 different methods. Okay, one is an explicit member list method, and the other one is the membership filter method. Okay, and the explicit listing method involves listing the members of the sparse set, whereas the membership filter method allows you to specify the sparse set members compactly through the use of a logical condition that members must satisfy. Okay. So when using the explicit member list method to specify a derived set's member list, you must explicitly list all the members you want to include in the set. And each listed member must be a member of the dense set formed from all the possible combinations of the parent sets. Okay. So returning to this example, if we had used an explicit member list in the definition of the derived set, allowed like this, then the allowed would not have full combination of 8 members, right? Instead, allowed would have only 3-member sparse set. So in this case, they are AM1, AN2, and BN1, right? So if you have a very large sparse set, then explicitly listing all the members could be a very time-consuming job, right? So in that case, you may use the membership filter method. So using the membership filter method of defining a derived sets member list involves specifying a logical condition that each potential set member must satisfy for inclusion in the final set. Okay? So in other words, you can look at the logical condition as a filter to keep out potential members that do not satisfy some criteria. Okay. Okay, so as an example of a membership filter, suppose you have already defined a set called trucks, okay? And each truck has an attribute called capacity. And suppose you'd like to derive a subset from trucks that contains only those trucks, so in this case, that have a hauling capacity, which is greater than 50,000 pounds, for example, okay? And by using the membership filter method, this can be done easily like that. So here, we use the vertical bar, right? So vertical bar is used to mark the beginning of a membership filter. And amperstate 1 is a set index placeholder. And the first prime primitive parent set member is plugged into amperstate 1. And this is the logical operator that means greater than. Okay, GT means greater than. And the logical operators that can be recognized by LINGO. So included here in this screen. So EQ is the equal, NE is not equal, GE is greater than or equal to, GT is greater than, LT is less than, LE is less than or equal to, okay? And LINGO provides a separate section called the data section, where all the values can be defined for different variables, okay? So similar to the set section, the data section always begins with a keyword, data, colon, and always end with another keyword and data, okay? So for example, in this case, this example defines values for each attribute separately, right? That is, we have 2 different attributes, X and Y, defined in the set, set 1, right? And the 3 values of X are set 2, 1, 2, and 3, where Y is set to 4, 5, and 6, right? It's very straightforward, right? And this example shows how one statement can be used to assign values to the 2 attributes simultaneously. So in this case, each row assigned different values to the X and Y pair, right? Okay, here are just list 4 different set looping functions that can be used in LINGO. So the set looping functions basically allow you to iterate through all the members of a set to perform some kind of operations, right? At 4 is used to generate constraints over members of a set. And at sum is probably the most frequently used set looping function. And of course, it computes the sums of expression over all the members of a set. And at min or at max, computes the minimum or maximum of an expression. Okay, so for example, in this case, the vendor of the vendor set has a corresponding demand, right? So we could sum up the values of the demand attribute by adding this expression after the data section, right? And the corresponding mass formulation would be like total demand is equal to sum over, right? Demand J, right? Here, demand J, and J takes the value from 1 to 5. How do we know? Up here, vendor set has only 5 different members, right? V1 through V5. So it has J goes from 1 to 5 because of the reason, okay? As a result, what value do you get? So if you add up 1, 2, 3, 4, 5 different values here, how much is that? It's going to be 19, okay? Okay, so next, suppose we want to sum the first 3 elements of the attribute demand. Then what you need to do is using the conditional qualifier on the set index, right? Like this. So we just need to add J, the subscript value J is equal to, sorry, J is less than or equal to 3, right? After the vertical bar, right? We specify this. So the corresponding mass formula should be demand 3 equals sum over demand J, but this time J goes from 1 to 3, right? Because it does say J has to be less than or equal to 3. So in this case, how much is that? The first 3 values, if you add up, 5 plus 1 plus 3, how much is that? 9, okay? Does it make sense? So by adding this, Lingo sum up the first 3 terms in demand, right? And omitting the 4th and 5th term. So for a total sum of 9, okay? Excuse me. Okay, the next is about the at max and at min. These functions are used to find the maximum value and the minimum value of an expression over the members of a set, right? So to find the minimum and the maximum demand, we just need to add these 2 expressions, right? Oh, okay. And next, just for the illustration purpose, suppose we want to compute the minimum and the maximum value, the first 3 elements of demand. Then what you need to do is just add this conditional qualifier, right? After the vertical bar, okay? That's the rule you need to follow, okay? So if so Lingo returns the minimum value and the maximum value of how much? It's going to be 5, right? And this is going to be 1, right? So considering only the first 3 values, the maximum value is going to be 5, and the minimum value is going to be 1, right? Okay. What is that? Okay. So to illustrate the use of at 4, so in this case, we have a primitive set of 4 trucks, right? With a single whole attribute, right? And we can use the at4 function to limit the amount hauled by each truck to here 2,500 pounds, right? So in this case, you can view the constraint lingo generates from this expression. I can show you this later, but basically with this expression, lingo can generate 4 different constraints. The first one is for the first car brand. So Ford is less than equal to 2,500, right? And then second constraint would be for GM, less than equal to 2,500. Third one, Toyota, less than equal to 2,500. And then whole for Hyundai, less than equal to 2,500. So it's cool, right? By using only one statement, we can generate 4 different constraints. Okay, so that's the powerful feature of lingo sets. Okay, imagine if you need to deal with 100 different car brands, then still lingo sets by expressing only one condition like this, only one the expression, you can still generate 100 different constraints like this. Okay, and in most larger models, you will encounter the need to loop over a set within another set looping function. So in this case, we have nested an at_sum function within an at4 function, okay? And yeah, and actually we're gonna deal with this kind of constraints that many times in the following examples. So don't worry too much at the moment, okay? And at_sum, at max, at min set looping functions can be nested within any set looping function. On the other hand, at4 functions may only be nested within another at4 functions, okay? Okay, and all the variables in our lingo models are considered to be non-negative and continuous unless otherwise specified, right? That's what he mentioned earlier. And lingo's 4 variable domain functions can be used to override the default domain for given variables. And these variables domain functions are at gin, at bin, at free, and at bound, okay? We already talked about this first 2, right? So at gin indicates the general integer that can take any positive integer values, right? At bin is the binary integer variable that can take only 2 different values, either 0 or 1, right? And free variable can take any positive or negative real values, and at bound can take any values within the specified bounds, okay? Okay, now let's revisit the chicken feed example. Okay, let me disable video so I can see the full screen. Okay. So I want you to recall that in this example, a farm manufactures chicken feed by mixing 3 different ingredients, right? And we were required to formulate an LP model to find the feed mix that has the minimum cost per each kilogram, right? And because in this case, the primary decision is to know how much of each ingredient should be included in the mixture, right? So that's why we define the decision variable like this way. X of I is the kilogram of each ingredient included in the mixture, right? And using this decision variable, we come up with this complete LP model. So objective function is to minimize the total cost, right? And we have series of constraints, right? Protein constraint and fat constraints, vitamins A, B constraints, and total weight of mixture constraint and sign restriction, right? Altogether, this is the complete LP model. Okay, now let's work on LINGO model using sets that we just discussed for this example. So let me get LINGO. Okay, so let me type LINGO. Okay, so remember, probably the first component we need to handle is the set section, right? And set section always start with set colon and then end with end set, right? Okay, we made a mistake. You know why? Because sets colon supposed to be in blue, but it's black because I made a mistake. I forgot S. So be careful, okay? So this syntax aware feature of LINGO is very useful, right? If you made a mistake, then easily you can indicate where you made a mistake, okay? Okay, so let's define ingredients, 3 different types of ingredients. So let's name the set ingredient. And because there are 3 different types of ingredients available in this case, so after slash 1, either 2, 3, or 1.3, either word, okay? And then after colon, what you need is just list the attribute, right? And these 3 types of ingredients associate 4 key nutrients, right? They are protein, fat, vitamin A, and vitamin B, right? And also cost of each ingredient. So let me put cost. And with each types of ingredients, we associate a decision variable, X variable, right? Which is equals the kilogram of each ingredient included in the mixture. So we complete defining the ingredients set. So here again, the set is given the set name ingredients, right? And that contains 3 members, right? And identified by 1, 2, 3, and attributes for each members. So called protein, fat, vitamin A's and B's, and cost value, and our decision variable X, right? So obviously this is going to be the primitive set, right? It's not derived set because it does not derive its members from other pre-existing sets. So obviously this is a primitive set, right? Next, we input the given data values for protein, fat, vitamins A and B, and cost for each ingredient. So I'm going to have data, right? Colon, and then end data. Okay. Make sure these are all in blue, right? Because that's the Lingo function keyword, right? So let's input the data values one by one. So what I'm going to do is I'm going to input all of these constraint coefficient values, okay? As well as the objective coefficient values. So first one is protein, and then fat, vitamin A, vitamin B, and then cost. So this is going to be 25, 45, 32. And fat's going to be 11, 10, 7, right? Oh. And then vitamins, 235, 160, 190. Vitamin B, 12, 6, 10. Cost, 0.55, 0.42, 0.38. Okay. Now we are ready to create the objective function. Okay. Oh, I forgot semicolon. Keep in mind that each statement in Lingo has to be terminated with semicolon. Okay. Okay, now let's input, let's create our objective function. Our objective function is very simple, minimize the total cost, right? So we are going to have min equals a sum, and then actually cost times X, right? That's going to be our objective function. Cost values are 0.55, 0.42, 0.38, and X values are X1, X2, X3. So it's like an inner product of that. But in order for us to use this expression, first of all, you need to indicate its then name first, which is ingredient up here, right? So I'm gonna copy ingredient and paste it here. And then you need to put a colon, okay, before you specify actual mass formula here. Okay. And then we're gonna close the parenthesis. So it does match this parenthesis. Once you open it, you have to close it, right? And then has to be greater than No, this is our objective function. So that's it, right? So don't forget to use semicolon to end the objective function. Now we are ready to type the each constraint one by one, okay? So basically we are going to input all of these constraints, okay? So let's just do this one by one. So we are going to use this format all the time, okay? First constraint is the protein constraint. Protein times X is greater than, equal to, how much? 35, okay? So we're gonna have 35 and then semicolon, right? So this is our protein constraint. So for easier readability, let's put some comments on that. That's the protein constraint. And then next constraint is going to be fat constraint. But see here, what happened? Suddenly we have green color here. That's because you forgot to close the previous statement, previous comment, right? So Lingo considers all of this as the comments, okay? Because you didn't close it, right? So don't forget the semicolon, okay? To terminate each statement and each comment, okay? Now, right after I put the semicolon, suddenly we got the normal statement, right? Like that. Now we are able to input fat constraint. What is that? Is greater than, equal to 8. And this is going to be fat. And then we are going to put the vitamins, no, still the fat constraint, right? Fat times X has to be less than, equal to 10. Still the fat, okay? And let's say minimum value, and here maximum value, okay? To distinguish. And then vitamin A, right? Maybe. And then vitamin B. Nine, right? Vitamin B. And then last one, the weight limit, right? So it's going to be summation of every X values has to be equal to 1 kilogram, right? So that's going to be the, let's say, total weight constraint. It's going to be equal to 1 kilogram. And then we'll put the ending mark, right? And then after that, if you press this button, or under this solver menu, if you press this, or press Control U, then instantaneously you're going to get the optimal value, optimal solution right away. So this is our objective, optimal objective function value, and optimal solutions are x1 value here, and x2 values, and x3 values down here, okay? later on, we are going to talk about the reduced cost and dual prices later. So don't worry at the moment. Okay. And what else? Oh, and earlier I mentioned that we should be able to view the constraints, math constraints Lingo generate from this expression. So if you go to solver menu and then choose generate and display model, then see, you can see what Lingo generated based on our Lingo sets model. Okay. So this is another great feature that you can track down the error messages. Okay. Or if you have some different optimal values than you expect, then you can check your math model like this way easily. Okay, so let's go back to our slide. Oh, I already provide this. Okay. Okay, so you can look at this, or this is exactly the same as I showed you, right? Okay, so next example, the post office scheduling. Actually, we did this last time, right? So let's reconsider this example. Just record your memory. In this example, post office wants to hire full-time employees, right? And one of the important assumptions is that each employee must work 5 consecutive days and then receives 2 days off. So for example, if an employee who starts work from Sunday, then he or she must work from Sunday through Thursday, right? Sunday, Monday, Tuesday, Wednesday, and Thursday. Those are the 5 consecutive days, right? And then must be off on Friday and Saturday, okay? And you are required to formulate an LP model that the post office can use to minimize the total number of the full-time employees, while at the same time meeting the daily requirements of these numbers, right? Okay, so we define the decision variable that indicates the number of employees beginning work on each day, right? And the day number 1 is set equals the Monday, day number 2, Tuesday, day number 3, Wednesdays, and so on. And using this decision variable, we come up with this complete LP model, right? Okay, so yeah, this is the input for Lingo using sets. So let's look at it line by line, okay? So first, we define the sets needed to solve the problem, right? So it defines the days of the week, Monday through Sunday. But okay, I think what's wrong with that? Okay, let me revise my slides. Okay, so this is the right information. Okay, so the first thing is we define the sets needed to solve the problem. So here we define the days of the week, right? Because there are 7 days in a week. That's we have only 7 different members, right? So these indicates that all of these attribute values, the requirement and start. Actually, in this case, start is our decision variable. So decision variable will have 7 different values, okay? I mean, we're going to have 7 different decision variables. And here, the RQMT stands for the requirement. So that's the number of workers needed for each day, right? So we're going to have 7 different values because of this. This set days will take only 7 different values, right? and the sets and the definitions of the sets. And next, we input the requirements for each day of the week, right? In the data section. And next, we create an objective function by summing the number of workers starting work on each day of the week. Okay, and next for each day of the week, we create the constraint that ensures the number of employees working that day is at least as large as the daily requirements, right? So, so for day number 1, for example, this part sums the total number of employees starting work of the values of J, satisfying these conditions, okay? J is greater than I plus 2, or J is less than equal to I, and J is greater than I minus 5, okay? So for example, this expression will generate the sum, which is this. So x1, x4, x5, x6, and x7, okay? So J value is the subscript value. So for I equals 1, considering the Monday constraint, J value will take 1, 4, 5, 6, and 7, okay? And now I'm going to show you how I got these conditions, okay? So let me open MS Word for that. Sorry, not good at that. This. Okay. And oh, I want to still look at. I want to use this condition. So let me resize the screen a little bit. Okay. Okay, so first on Monday. So if we consider Monday constraint, then on Monday, which is I value equals 1, right? So on Monday, who's working? if you look at this, on Monday, only these people works, right? X1, X4, X5, X6, and X7 people, right? X1 people is the number of the employees who started work on Monday, right? And who is X4? That is the number of employees starting work on Thursday, right? So these people work from Thursday, Friday, Saturday, Sunday, and Monday, and then Tuesday, Wednesday off, right? So that's why X4 is still included, right? Likewise, X5, X6, and X7, so all work on Monday. So we need to have these subscript values of 1, 4, 5, 6, 7 for I equals 1, okay? So we want to have J values 1, 4, 5, 6, and 7, right? That's for Monday. So how do you get this value of 1 for J? If J is equal to I, which is 1, then we can get J value equals 1, right? Or if J value is greater than, let's say, I plus 2. Since I value is currently 1, 1 plus 2 is 3. So J is greater than 3. That's why we're going to have these 4 values, right? Because earlier we defined all of the X variable can take only these 7 different decision variables, right? We are going to have only these 7 different decision variables, which means the subscript values of the decision variable will take only these 7 different values. In other words, X1, X2, X3, X4, 5, 6, and X7. That's the only available decision variables, right? That we can consider. That's why we can get this, right? So how about on Tuesday? If I equals 2, then what value do we have for J? If I equals 2, then J must be 1, 2, 5, 6, 7, right? So in that case, J must be 1, 2, 5, 6, 7. So let's use the previous condition. J equals I. In that case, J value is going to be 2, right? Or J is greater than I plus 2. Then in that case, 2 plus 2 is 4. J is greater than 4. That's why you have these 3 values. Then how do you get value of 1? If we modify this first condition to J is less than equal to I, then we can get these 2 values, right? Same here, up here, doesn't matter. J can be less than or equal to 1. Then still, we're going to have the value of 1, right? Here. And what about on Wednesday, which is I equals 3? Then we must have J is going to be 1, 2, 3, and 6, 7, right? From here. 1, 2, 3, 6, 7, right? So does this condition still work? J is less than equal to I, which is 3. In a way, we can generate these first 3 values, or J is greater than I plus 2. I is 3. 3 plus 2 is 5. So J is greater than 5. So that we're going to have these 2 values. So that still work, right? So now let's move on to Thursday. For the case of I equals 4, then J must be 1, 2, 3, 4, and 7, right? So with this constraint, we're going to have these first 4 values. And with this, we're going to have last value, right? How about Friday? So I equals 5. J is going to be 1, 2, 3, 4, and 5. Does this work? So the first constraint, J is less than or equal to I. I is equal to 5. So from this first constraint, we can get all of these 5 values. And what about this? J is greater than I plus 2. I is 5. 5 plus 2 is 7. But as a default, J cannot take the value which is greater than 7, right? Because there is only 7 days in a week. So that's why we defined the what is that? The days set as only 7 members, right? Monday through Sunday. So here we can see that for the case of Friday, the second constraint is redundant, okay? Oh, the cursor is up there. Oh. Cut this, then it's up here. No way. Hopefully I can do this. No. Let me insert a couple different pages. And then here, paste. Okay, now it's working. Okay, so for the is that the Thursday constraint? What's going on? Is that deleted? Okay, let me just rewrite. So on Friday, I equals 5. We have J equals, what was that? J was 1, 2, 3, 4, and 5, right? And what about on Saturday? It says I equals 6. Then J is going to be 2, 3, 4, 5, and 6. And let's still use the same condition, which is J is less than or equal to I, or J is greater than I plus 2. Is that right? Okay, let's see. So with this condition, what do we have? We're going to have 1, 2, 3, 4, 5, and 6, right? But we shouldn't have the value of 1. So that's going to be the problem, right? And again, this is going to be redundant in this case, right? So this means that we need to add more constraint. In a way, the value of 1 will be excluded for the case of I equals 6. So how do you do that? In this case, if you add and j is greater than what? J is greater than I minus 5. So in this case, I is 6, right? 6 minus 5, that is 1. So if j is greater than 1 and j is less than equal to I, then the value of 1 will be excluded. Is that right? So let's update our condition here. J is less than equal to I, and j is greater than I minus 5. Or j is greater than I plus 2. That's our condition so far. Let's see if this condition works for Sunday, which is I equals 7. On Sunday, j value must be 3, 4, 5, 6, 7, right? So j is going to be 3, 4, 5, 6, 7. So with this, j can take 1, 2, 3, 4, 5, 6, 7. How about this? If you add this restriction, j must be greater than 7 minus 5, which is 2. J must be greater than 2. That's why only these 5 values are considered, okay, included for j. Again, in this case, the second condition is redundant, okay? So that's why this is the one that we included in our LINGO model down here, okay? See here, j is greater than I plus 2. Okay, I put this condition first. J is greater than I plus 2, right? Or, right? Or j is less than equal to I, which is this. And j is greater than I minus 5. So I put j is greater than I minus 5, okay? So that's why I put this conditional qualifier after the vertical bar here, okay? And this part ensures that the total number of employees working on each day is at least as large as the total number needed for that day, which is the requirement, right, for each day. So, of course, if you run this, so let me copy this and open the new window and then paste this, okay? And then I'm gonna run this, then I got the optimal solution right away, okay? And again, if you want to see the math formula generated from this LINGO sets, then go to solver generate display model. Then we've got our Lingo model, right? Like that mathematical model formulation like this. Of course, this is exactly same as what you have here. Okay, so for the Monday constraint, x1, x4, 5, 6, and 7. Here, the Monday constraint is x1, start 1, start 4, start 5, start 6, and start 7, right? So those are match each other. So with this example, we've seen that Lingo enables us to create 7 different constraints, right? Monday through Sunday constraint by typing just one line, this one statement, right? This is because Lingo can allow us to group the similar objects together into sets. So in our example, such group would be the days, right? Okay, and of course, to indicate that each variable must equal the non-negative integer, we've used the @gen operator, general integer restriction, right here. For each days, we need to put this, right? Then, as you can see here, just by adding this one statement, Lingo can generate these 7 different variable, general integer variable restrictions, right? So we use a @gen operator, okay? I think, yeah, I think, yeah, that's all for today. So I'm gonna stop here. And next time, we're going to continue talk about Lingo sets. And I'm gonna give you several more examples on that, okay? So thank you so much, guys. Okay, bye-bye.